All right, Jesus, I know you weren't here in the first part of the class. Hopefully you'll be coming in, but if you're not, I forgot to turn on the screencast-o-matic. So we're just starting now, but we covered pages 163 and 164 before I remembered to turn that on. So sorry you won't hear anything from them, but we're beginning now on page 165. What you see on the board is theorem 4.4, which is properties of scalar multiplication on page 164. But we're now going to move to 165. So sorry, I'm going to have to shut this down to do 165. Sorry, I just forgot to turn it on today. I don't know why, but it's been a rough week. I'll put it that way. Now, top of 165 it says, the remaining examples in this section describe some sets with operations that do not form vector spaces. Okay? Now, to show that a set is not a vector space, you only need one axiom that is not satisfied. Remember, you have 10 axioms that you can do. Find any one that is not satisfied by this vector space. Now, let me back up the earlier sentence. The remaining examples of this section describe some sets with operations that do not form a vector space. Now, the reason I wanted to read that again, sometimes it's the set's fault, okay? You may have a set that just doesn't fit the bill. It doesn't meet all the axioms, and therefore it won't work. Other times it may be the operations that don't work, okay? Because if you choose some, I hate to say it this way, but in my mind it is, some stupid definition for scalar addition or vector addition or scalar multiplication that just doesn't work all the time, guess what? That's not going to be a vector space. And you get to choose the definition. A lot of times we'll say the standard definition. Standard definition may work most of the time, but on some sets it may not work. So it can be either the set's fault, or it could be the definition's fault, or it could be the combination of the set and the definition's fault. Maybe neither one of them would work. So here are some sets that are not vector spaces. They definitely are sets, and they're very legitimate sets. Okay? Example 6. The set of all integers, and I want to write the set symbol down. Okay? So the set of all integers with standard operations. So we're not going to put anything stupid out there. With standard operations, how you add and how you multiply, okay, do not form a vector space. They're certainly a set. They're a closed set in addition. They're a closed set in multiplication. They have a zero vector. They have lots of things work. Okay? I actually said something wrong there. Okay? They're closed under scalar. They're closed under addition. You add the integers together, you get an integer. Subtract integers from integers, you get an integer. However, remember it said with standard operations, standard operation is this. Your scalar multiplication would be that, let me see, let me use I as a representative of an integer. If you did C times I, the standard operation for any real number C. Now that's your standard operation. Nothing funny and fishy and unique or strange about this. That's standard. For any C times I, guess what? You won't necessarily be closed under scalar multiplication because C is any real number. And the one they give in the book, what if C was 1/2? 1/2 of, say, 3, which is an integer, would be 3/2. 3/2 is not an integer. It's not closed under scalar multiplication with this standard operation. Now, if you said we're going to find this C to be, in your scalar multiplication, any integer, yeah, you might be able to get that to work at least somewhatly. I think probably it would, but that's not your standard scalar multiplication. Scalar multiplication usually is for any real number C multiplied by an element in your set. You're always going to get an element in the set. This one you did not. 3's in the set, standard real number, 1/2 pi, square root of 3, multiply that by any integer, you're not necessarily going to get an integer. The reason I threw in square root of 3 and pi, it doesn't matter what integer you put there. The 1/2, what if you chose an even integer? That would work. But you see, you don't get to choose them. It has to work for every entry, every set member of the set. And certainly your odd members of the set would not work. Okay. So that was example 6. I hope that's making sense. Set of all integers is definitely a set, but it's just not a vector space under the standard definitions. Now, what if we said the set of all second degree polynomials? And I'm going to write it like that. Set of all, see, it writes so much better if I don't pick up the pen. Second degree polynomials. Okay, that's certainly a set. And you might say, wait a minute, we've had that set before. No, we haven't. We had a set of all second degrees or less polynomials. We had the set of all polynomials. Those were all vector spaces, okay? But this is a second set of all second degree polynomials. So let's just pick one. 3x squared plus 2x minus 7. That's a second degree polynomial. So let's say we're going to use, and this is with the standard definitions of your vector addition. This is a vector, remember, and scalar multiplication. Okay? So, what if you were to add to this second degree polynomial this second degree polynomial? Minus 3x squared plus 2x minus 14. Okay? I didn't have to choose anything there. The special note was this. If you add those two together, you get 4x minus 21. Okay? Guess what? This is not a second degree polynomial. So therefore, it's not closed under standard vector addition, where you add the two and yeah. Those are definitely both second degree polynomials. You add them together and you get a polynomial that's not second degree. Now sure, you can't get one that's any higher, but you can get those that are lower, and that's not a second degree. Now, that's why all second degree polynomials or less would be a vector space, because that includes any that would have canceling in them. Okay. Now, let's look at the next one. I'm going to clear this one just in case this next one may take more room. Let V, which usually mean a vector space, equal R2. Well, we know R2 is a vector space. That's a set of all ordered pairs of real numbers with standard operations of addition okay, and the non-standard operation of scalar multiplication. Okay, here is the one they use. Now, to me this is just stupid, but they do it. What if they say your scalar multiplication of this R2 set of all ordered pairs, so this would be x1, y1, x2, I think that's what they use in the book. Yeah, but let's give this scalar multiplication, and this is what I meant when we said that V equal R2, we think of that as a vector space. And we named it V, we said R2, we said R2. But if you go back to the table that we just did a couple pages ago, it says the operations are the standard operations in each case. Okay? Here we're given a non-standard operation. And here is your non-standard vector scalar multiplication. Let's say that C of x1, x2, the standard would be cx1 comma cx2. But there's nothing that prevents you from giving a different one. And here's what the different one is. That it's cx1. So do that as if it's standard, but make the other one 0. Okay? Now, strange, in fact, in my mind, stupid definition for your scalar operation, scalar multiplication. Okay? But why would that prevent it from being a vector space? Well, let's do this. That it certainly is a vector in R2, okay, to multiply that. There was no guarantee that you have to have all the vectors in R2, but it was. So this is a vector in R2, okay? Now, that is right there. That is a vector in R2 because it's that scalar, okay? My wife just sent me a text. I didn't have time to read it all, but we're close enough to the end that I'll deal with that later. See, wait, what time do we end? 12:45, isn't it? I don't know if it's anemia or old age or what. Let me think again. Yeah, this class goes till from 11:30 to 12:45. That's right. I've seen the people out there working. I didn't know who it was, but that's what her text was. Okay. Whatever her text was, it was okay. All right. Now let's get back to it. This is a vector in R2, right? That's our definition of scalar multiplication, okay? Here's also a vector in R2, x1. Let's see, maybe this isn't going right. No, that's not it. I thought I had it before the phone message. Now I can't remember what I was going to do with it. Okay, let me not waste too much time on it. That's right. The very last axiom that we have in those 10, if you remember that one, okay, the very last axiom was the one they called the multiplicative. I called it the multiplicative identity element. They called it the scalar identity, okay, that 1 times a vector u has to equal vector u. All the first 9 fit. It's that last one. And why is that true? Because what if you have 1 times x1, x2, well, I could have called that u1 and u2, but since I've already written, I'll do that. According to this scalar multiple thing, that would be x1, 0. Okay, somewhere there's supposed to be a comma in there. And that is not equal to x1, x2 for every x2 that you have out there. Only when x2 is equal to 0, but that was for any vector in the space. So your multiplicative identity element does not exist, does not work with that definition. Normally that would be a vector space. R2 is usually a vector space using the standard operations. But like I said before, sometimes it's the space's fault, other times it's the definition fault. Okay? This one, to me, that's a stupid definition. So therefore that keeps it from, I can't imagine many vector spaces that would make any sense in. So why would they even propose it? Okay? But they did, and it is legitimate. Okay. And they have the statement at the bottom. They say, do not be confused by the notation used for the scalar multiplication in example 8. In writing C of x1, x2 equals C1, Cx1, 0, the scalar multiple of x1, x2 by C is defined to be that in that example. That's not saying that changes it for all time for all problems. It's just what I consider a stupid definition, okay? And that wipes it out from being a vector space then with that definition. With standard definition, yeah, R2 is always that. That finally finished, and that was a terrible way to finish, I think, section 4.2. Homework exercises here. Any of the odds 1 through 5, they're all at calcchat.com. Any of the odds 7 through 11, they're all at Calc Chat. Any of the odds 13 through 35, they're all at Calc Chat. Okay, there's a lot of them too. I would say any of the odds 37 through 47, they should all be at Calc Chat. 49 should be at Calc Chat, and 51 should be at Calc Chat. Okay, so let's move on to, I'm warmed up a little bit, but I'm still awfully chilly. Not sure drinking water is a good solution to that, but I feel like I need to replenish that too. Let's move on to section 4.3. 4.2 was talking and defining what were vector spaces. 4.3 is talking about something called a subspace of a vector space. Now, let's get some nomenclature straight. And I don't know how many of you, either of you, no, I guess it's just Kira now, because I think James has dropped out somewhere. Let me just make sure that he's, I can't see him. Nope, yep, just got Kira. Hope he's not in the waiting list, no, waiting room. I don't know why. Well, he must have either lost signal or had to go. I don't know. Okay. I don't know how much you've done with sets. I know we always talk about sets and people deal with it. Back when I was growing up, this was called modern math, okay? They came up with this whole concept of sets and, dealing with sets. A lot of people didn't like it, but a lot of people didn't use it anymore, whatever. Okay. But let me give you a little bit of the nomenclature of sets. Okay? For instance, the set of counting numbers are also called natural numbers. That's 1, 2, 3, 4, 5, 6, 7. The numbers we use to count with. That's a set of numbers. Okay? It can either be called natural numbers or counting numbers. Okay. If you add the number 0 to that set, you form a new set, and that's called the whole numbers. Okay? Now, the counting numbers, or the natural numbers, is a subset of whole numbers, because every counting number is also a whole number. But the whole numbers is not a subset of counting numbers, because 0 is not included in the counting numbers. So that's what we mean by a subset. Every element in the, quote, smaller set must be in the bigger set. That's what makes it a subset. Okay? Now, in this section, we're going to be talking about subspaces. Okay? Now let's think back. What is a vector space? A vector space is a set. But that set has to follow the 10 axioms. Okay? It has to. All 10 of those must meet if it's going to be a vector space. You can have all sorts of sets out there, but not all of them are vector spaces. Okay? Now, when you define that vector space, you also have to give the definition for what your scalar addition is, your vector addition is, and scalar multiplication is. And then it has to meet those 10 axioms for those two definitions as well. Okay. Now, what do we mean by subspace? I'm going to write out that definition, and this one I may actually type out. Not that my typing's very good, but it'll be easier to read. Okay, so I'm going to go to text here and get my text box set up here and go from here. This is the definition. Goodness gracious, I don't know why these kinds of things happen. but I've got so many cords here, the one that I on my headset, and it gets underneath the chair and then it's stuck. I always try to have it in my lap so it doesn't happen, but this is a definition of a subspace of a vector space. Okay, not quite the same, similar but not quite the same of what a subset is of a set. Okay, so here's what it is. A non-empty subset, here's that subset W, well, W of a vector space is a subspace of V when W is a vector maybe I should have written the longhand. I can't. Goodness gracious. Why does that W always come out as an ampersand? Okay. My finger's too long. Okay. Oh man, I'm so hungry and cold. Okay. When W is a vector space under the operations of addition and scalar multiplication, defined in V. Okay. I don't know why my fingers are overreaching today. Usually they don't. Okay, so there's your definition of a subspace. A non-empty subset W of a vector space V is a subspace of V when W is a vector space under, I don't know why the D didn't type, under the operations of addition and scalar multiplication defined in V. Okay, now let's get a few things down. Number one, it has to be a subset. Okay, W has to be a subset of V. Remember, V, the vector space, is a set. It is a set. It's just a set that meets those 10 criteria under those two definitions of your operations, addition and scalar multiplication. So vector space V is a set. Set W is a subset of V, meaning everything that's in W has to also be in V. Now, what's this deal about non-empty? Technically, an empty set is a subset of any other set, okay? In other words, a set with no entries is a subset of a set with entries, okay? So I'm sorry, I said that wrong. An empty set is a subset of all sets, okay? So this is saying you can't have an empty set being a subspace because an empty set can't meet all the requirements. So basically this is saying just being a subset alone is not enough. It has to be a subset, but number one, it can't be an empty set, which is by definition also a subset. So that's sort of a weird little feature, but it has to be set. So it has to be a non-empty subset, okay, of the vector space. But that's not enough. It must also be itself a vector space using those same operations of addition and scalar multiplication that you had defined in V. Now, if they're the standard operations, that's fine. You can just go with them. But if that vector space V had one of those weird non-sum standard thing, but kept being a vector space, then the subset W of that V must also be a vector space using those same weird definitions of addition and scalar multiplication. Okay, so example 1, here is a set. Okay, I think I'll go to my draw mode here. I'm sorry. I go through being cold, then tired. I can't believe I ever would say this. I can't wait for that infusion because I'm hoping it's going to make me feel so much better. Transfusion. Okay. I should have brought up another soda. I'm going to have to eat me something. I'm sorry. I wish I brought up something that was softer to eat. Sorry about the chewing. Okay. Now, here's example 1. We know what R3 is. Goodness gracious, this thing is so bizarre. It barely, sometimes it won't write at all, and other times it hardly even touches the screen and it writes. Well, that cleared out even my text. Sorry about that. Thought it was just going to clear out the drawing. Okay. We all know that R3, goodness gracious, this is so bizarre. R3 is a vector space. VS is vector space. Okay? You know it is under your standard definitions for vector addition and scalar multiplication. It is a vector space. Now, here is a subset of that vector space. Set W. Okay? And here's what set W is. It's the set, and R3 is a set of all ordered triplets. Okay? So this is a set of all ordered triplets, x sub 1, comma, 0, comma, x sub 3. Such that x sub 1 and x sub 3 are real numbers. Sorry, I'm writing, but it's that. That's your subset. Okay? Certainly a subset of R3, because R3 would be the set of all ordered triplets, x1, x2, x3. So this is a subset of that one. x1, 0, x3. Okay? Where x1 and x3 are all real numbers. Okay. Now, the question is this also a subspace? We know it's a subset, and this would be W is a subset of R3. We know it is. It's an ordered triplet, and this is a set of all ordered triplets. Okay? Is it also a subspace of R3? I think I'll write it here. Is it a subspace? That's the question. It is a subset. Is it a subspace of R3 with the standard operations? it's certainly not the same space. If that was an X2 in there, that would be R3, but it's not. This is a subspace. Now, well, it's a subset for sure. Is it a subspace with the standard operations we've named before? Okay, when you add two order triplets together, you add the corresponding components, and that's also in our 3. Okay, now, and your scalar multiplication would be multiply any real number by those that ordered triplet, and you also that would be the same as that real number times each of the components. That's your standard operations. Okay, vector addition, scalar multiplication. So is this a vector? Is this a subspace? Okay, we know it's a subset, so the first requirement is met. We know it's non-empty, so that requirement is met. The question is it a vector space? Now, you could go through all 10, and sure enough, if you add a vector in W to any other vector in W, say y1, 0, y3, you get another vector in W, because that would be x1 plus y1, comma, 0 plus 0, which is 0, comma, x3 plus y3, close it out. That's a vector in W, okay? And you can go through every one of the thing, associative property, the distributive property, the commutative property, every one of them that's there. The 0 vector is there because that would be, where's my pen here? It's somewhere over here. There it is. 0, 0, 0 is certainly in W because that middle element is 0. And these two are also in that. So your 0 vector is there. 1 times this will still give you that. So that 10th one that threw us last time, that's still there. Every one of them is met. So yes, this is a subspace. Now, physically, we know it's a subspace because physically, what is this? This would be every element on the XZ plane. R3 is all space. The XZ plane, where X may be in this direction, Z in that direction, the XZ plane would be here. That's basically a value that's just like R2. R2 is a space, a vector space, so therefore this W is a vector space. Okay, so that's really all you have to, you can picture that. The set W is non-empty because it contains the 0 vector. Graphically, it's represented as the XY plane, and the XY plane is a vector space. Okay, I'm sorry, XZ plane, not XY plane, XZ plane. Okay, now, here is a theorem, which is a test for a subspace, and this basically narrows it down so you really don't have to do all 10 anymore. So I'm going to clear this out of the way, and I believe I can type this in maybe a little bit better than I can write it. My typing leaves a lot to be desired too. Okay, if W is a non-empty subset I'm sorry. I'm blaming all this on this stinking anemia. I just cannot get warm. So I'm sorry. Oh, we got 3 minutes. I'll wait 3 minutes. I was going to go turn up the thermostat again. I'm just so sorry. If W is a non-empty subset of a vector space V, then, that's V, aggravates me, then W is a subspace of V if and only if the two closure conditions listed below hold. Okay, the first of these, if I can't write bold, this is a bold, U and V are in W, then U plus V is in W. 2, if U, and that should be bold, is in W, and let's see, they don't have a comma there. C is any scalar, then CU is in W. Okay, let's string this out a little bit so it reads a little bit better. I can't get it to move. There we go. And somehow that expanded more than I wanted it to. So here's what we got. If W is a non-empty subset of the vector space V, then W is a subspace of V if and only if the two, and for some reason my space bar didn't work there, the two closure conditions listed below hold. So first, if U and V are both in W, then U plus V is in W. If that's the case, you're okay. And this next one should be capitalized. I don't know why that didn't happen. If U is in W and C is any scalar, then CU is also in W. So that means we don't have to go through all the commutative, associative, distributive, and all those kinds of things. Those, as the book calls them, they're inherited. They come with the game. If these two are met, then you're okay. Okay? That's going to shorten our search down pretty big. But I would like to say this, okay? Always check for your zero vector. It is kinda in here, but it's not explicit. That's usually one that'll trip you up just about as fast as any of them, okay? And if the zero vector is not, if there's, just like checking for the zero vector, that one that caught us on that other one, that 1 times U is equal to U, well, that's here in this one, so make sure it's there too. That's one so simple you don't usually think about, so make sure that's there too. All right, I think we have gone over time. Sorry about that. No extra charge though. Let's see, let me mark where we left off. That was there. So we'll pick up, I think I will mention again the thing about the zero subspace. We didn't really talk about that. So that's where we'll pick up on page 169. Homework exercises in this section will be in 4.3 on page 173. I think it will be able to do any of the odds 1 through 5. And maybe some of the odds 7 through 19. But if some of those get too esoteric or weird, we will no, let's see, let's just do 1 through 5, okay, because we didn't really do some that are not. We'll do those later. Okay, we did it in the last section. Any questions? Okay, you've already heard me say probably several times now, be safe. Okay, please be safe. I know Thanksgiving is coming up, Thanksgiving week. You know we don't have any classes. It's a great time normally to be with family, friends, and enjoy good food and good times. This year is so bizarre. We're not going anywhere. Well, we're supposed to go up to Huntsville to celebrate my wife's mother's 84th birthday on Friday after Thanksgiving. We were just going to go up for the day, but now with my health situation being like it is and COVID just still being outrageous, we may or may not go. So I don't know. But we're not having anyone in. We always have people in for Thanksgiving. We're not this year. So I know, do whatever you have to do, but please be safe. Be as careful as possible. Have a good Thanksgiving, but really what we're interested in is having good Thanksgivings in the future too with those same people, so don't put anybody at risk. We don't want to lose anyone because of this virus. You know it's going to happen to some people somewhere, somehow, because it's spreading like crazy. Do everything you can not to have it happen to you. So be careful and be safe. Any questions? Okay, well, have a good Thanksgiving week. We'll see you the Monday after Thanksgiving in other classes, and then we'll see you again in this class on Tuesday. Take care. Bye-bye.